Hello everyone. I welcome for analog electronics lab session. Today we'll try to discuss the application of diode. You all studied the application of diode in basic electronics. So basically there are two applications. So one is diode can be used as a switch, and the one more application of diode, it can be used as a rectifying element in a rectifier. Now where is the application of what is the application of rectifier? Like rectifier, so we use rectifier in power supply design. When it comes to power supply, regulated power supply, there we need to get a constant voltage. We need to supply a constant voltage. We need to get a regulated voltage. To get that regulated voltage, we are going to use the rectifier. So that is a main component or main block in the case of power supply design. But to design rectifier, again we need a diode. Like now what is the function of diode in that rectifier? Like the rectifier, it's a device which converts AC into pulsating DC. Now, the diode actually, where we use diode as a rectifying element in the rectifier, so that it converts AC into pulsating DC. In analog electronics itself, you are going to study the clipper circuit, and if you take so rectifier, you take a off-wave rectifier. Off-wave rectifier, it's the best example for the positive. It's a negative clipper where in that negative clipper, the negative off cycle will go into clipper. If you take off-wave rectifier, where it converts AC into pulsating DC during one off cycle, that means it will convert AC into pulsating DC during positive off cycle. For negative off cycle, it will not convert, where for negative off cycle, diode is off. I will show you the simulation. So that is the first experiment. So we'll do in analog electronic circuit. So I'll take off a rectifier circuit. Let's see how to build an off-wave rectifier circuit. And like there are three different types of rectifiers, like off-wave rectifier, full-wave rectifier, and bridge rectifier. Now to design a power supply, we prefer a bridge rectifier. I will tell you later why we prefer bridge rectifier. Even though full-wave rectifier is very simple, and it is less costly compared to less cost compared to a bridge rectifier. Even though if you see the circuit, the circuit is also very simple. Full-wave rectifier circuit is also very simple, but still we prefer bridge rectifier. I will tell you what is the reason for that. And you take efficiency and ripple factor, those two parameters also same. And three important parameters we should take in the case of rectifier. Like the first one is efficiency, the second one is what, ripple factor, third one is PAV. PAV is very very important. So the PIV, like its peak inverse voltage, it refers to the maximum reverse voltage during reverse biasing condition of a diode. So that is what we say PIV. Suppose if always you remember while designing any rectifier circuit, this PIV parameter should be very less, so that the diode diode will going to withstand. Suppose if PIV is less, if PIV is more, and the diode so it will not withstand, diode will going to become damaged. So that value should be very less. So if you take a full-wave rectifier, in the full-wave rectifier, PAV is very large, and that is the reason why we avoid the full-wave rectifier. So now let's take let's see how to design of a rectifier. Now to design a rectifier, so what components we need? As I said already, like we need a diode. So I'll take a diode. Then before diode, we need one the transformer. Like you all know the three different types of transformers, like 1:1 transformer, step up transformer, step down transformer. Anyhow, here we are converting AC into DC, so we don't want AC again. That means the primary will be getting 230 volts. You all know in India, so the standard voltage for home appliance will be 230 volts and 50 hertz. And when you get 230 volts, that voltage is very very large, and you need to reduce that voltage. You can't give 230 volts to the diode, because the next block is diode. Simply you can't give 230 volts. Diode will break. Suppose if you give 230 volts, and diode will not convert that much of AC voltage into DC, so pulsating DC. So what we should do here, we are supposed to reduce the voltage we should reduce primary voltage. Now what we should do, what type of transformer we should choose. So we should choose step down transformer. So you should take care so how much voltage you need in the secondary. I mean to say that depending upon your application, say for example I just need so the 10 volt power supply, then you're supposed to get, at least you need to get 12 volt voltage, AC voltage in the secondary. So like that you need to adjust, and that voltage it can be designed by choosing turns ratio. That the turns ratio matters. So we will see how to design an off-wave rectifier. Now let's take the off-wave rectifier. For that we need a transformer. I'll take a transformer first. So let's take a transformer. So yeah, let's take a transformer. So this one is end-to-end transformer, and center tap is used for full wave rectifier. We will see that. And now if you remember of a rectifier circuit where it contains only one diode, right? So in the full wave it contains two diodes, in the bridge it contains four diodes. Now here where that diode is actually connected series with respect to secondary and as well as what load. I just want to connect here load and as well as what diode. Let's see that. So we will connect it later. Now I'll just see how to put the turns ratio here. Okay, so now so what is the primary voltage? The primary voltage is 230. I just want to apply 230 volts. Now let's take one on the battery. So I'm going to use AC. So now let's provide primary voltage. So I'm providing primary voltage. Yes, so now the primary voltage is given from this source, and I just want to see the waveform of this particular the primary voltage. So for that I'll take a CRO. Let's take a CRO. I think this is 3D view, the virtual view of instruments. Yes, and let's select the voltage here. Now let's take 230. So I'll keep 50 hertz. So no need to change that. Suppose if you simulate, you can see here. You can see I'll just auto set. I will adjust and I will trigger. I will stop the curve. Let's see how much voltage. See, you can see 230 volts. Okay. So 230. Now we are applying 230 volts here. Okay. You can see here 230. The peak to peak. Here also you can minus 230. So input, now it's 230, and here also 230. Input is 230. That means the primary voltage we are giving 230. So now let's build the circuit again. So now what I need, I need diode now. So I'll just zoom out. Okay. Now I need a diode. Let's take a diode here. Yeah, diode here. I'll take a diode. Let's rotate, because I need to I need a positive voltage. So I'll just rotate the diode. Yes. So now I'll give it some gap. Fine. I just need one load here. Let's take load. I will put some value. Let's take, okay, I'll keep 620 only. Anything it's fine. So now here I'll just connect. You can see as I said now like it looks like a series circuit. The secondary and your diode and source are connected in series. This circuit, this is actually series connection with respect to source. This is your secondary and this is your primary. Now I just need a 12 volts. Now that what I said, like depending upon your application you can choose the secondary voltage. I just tell you how to calculate that. You all know that the voltage transformation, or the relationship between voltage and turns ratio. So that is nothing but V2 divided by V1 will be equal to what? N2 divided by N1. In other words, V2 divided by V1, and that will be equal to N. Here we don't know. So what is N1 and N2? So I can write that formula like this also, like V2 by V1 is equal to, it's N. Now V2 I need 12. So 12 I'll take, divided by, and what is the input? V1, it's 230. Let's divide. You will be getting turns ratio. I got 0.05217. Let's put here. I'll put it's 1. That means it's 1:1 transformer. Like as I said that there are 3 different types of transformers. 1:1 where whatever the input you're going to apply will be getting at the secondary and step up, like where the turns ratio will going to drop, so that secondary voltage will be less. Sorry, step up means secondary voltage is more, step down, so secondary voltage is less. We need step down transformer. So now I got turns ratio 0.052521739. I'll repeat again how to calculate this. We all know what is the primary voltage is 230. We don't know what is the secondary voltage, and we don't know the turns ratio. Now the relationship between voltage and turns ratio is V2 by V1, that will be equal to N. In other words, V2 by V1 is equal to N2 by N1. We don't know both N2 and N1, so I'll just take a N. So that formula can be written like this also. You all know. I think you just remember basic electronics or basic electrical. You all study transformers in electrical. So where we can write V2 by V1 is equal to, it's N, where V2, now I'll repeat again, V2 is 12. I just need 12 volts divided by 230, and you will be getting 0.05217. So what you should do here, you should put here, okay, this is a turn ratio 0.0521739. You can change, suppose if you want 10, so what you should do here, so 10 divided by 230, so you will be getting turns ratio 0.0434. So in the secondary you will get 10 volts. So that is your wish. Okay, so now again let's check this. What is the voltage we are getting? You can see here. I'll just slow down this. Yeah, the maximum we are getting 11.99. You all know, like the transformer, even though it is simulator, still there is a what losses, transformer losses. Just remember your electrical. So there is a winding losses in the transformer. Because of that, you will not get exactly 12 volts. You will not get that. So that coupling is not possible. Effective coupling is not possible in the case of transformer. So I'm getting the 12 volts here. So this voltage you can change. Suppose if you want to design a power supply around 14 volts, then you can't you can't use 12 volts. That voltage should be more. Suppose if you are designing for 14 volts, then this voltage should be more. Okay, so now this one is over. Now what I want to do here, I just want to connect on the output side, I just want to connect one more CRO. Let's copy this. Sorry. Okay, I'll take one more CRO. Let's take one more CRO. Let's connect here. And this is connected here. So this is okay, fine. Now let's simulate now. Okay, you can see here, reduce this. I'll reduce this. Let's make a 4. Okay, just make it. So let's make it 10, and I will stop this and just trigger. Now let's see. So what is the voltage we're getting? You can see here. You can see how much voltage you're getting. You're getting 11.3, 11.4. Now what happened actually? The remaining voltage you can see here. We will come back to this later. See, I'm using here the diode. It will be having some cut-in voltage. You can see here the diode is having cut-in voltage 800 milli, that means 0.8 volts. Now what happens during positive off cycle, this diode will conduct, no doubt, and whatever the input you are going to get, you will be getting at the output side. Say for example, I am applying the maximum voltage 12 volts, and now what happens? So this 12 volts will appear across what load, but entire the voltage will not appear across what load. Because so this diode is having some voltage drop, so that voltage drop will be subtracted from this voltage. I think you can see here it's how much, 11.9. we're getting around 12 we are getting, but this diode will not pass entire 12 volts across load, because the diode is having some cut-in voltage, and the cut-in voltage will be getting during forward biasing condition. You can see here, see you will be you can see at this point you are getting some positive voltage, then you're getting zero. When you're going to get zero, when you get negative off cycle, so this will going to become zero. If you get positive off cycle, again now the positive off cycle is started, you're getting some voltage, again you will getting zero. You can observe, keep observing, keep observing. Yes, you got zero. That means the negative off cycle is started. When it falls less than 12 volts, the negative off cycle started actually. Yeah, you can see again it's rising during positive off cycle. You're getting, see, around the maximum voltage is 11.3. you're getting, again it will become zero. Again you can check for positive off cycle, again it will going to give some voltage. You can see just right. Yeah, now it's started, positive off cycle is started. And meanwhile we will be getting the waveform here. Let's check the waveform, you will understand. You can see here, see, during positive off cycle we got, the voltage. During negative off cycle we're not getting anything. I said one thing like off-wave rectifier, we can also call it as negative clipper, because in that negative clipper, the negative clipper will clips negative off cycle. You can see here we're not getting any negative off cycle. That means negative off cycle is clipped, so we'll be getting only positive off cycle. So this off-wave rectifier, it converts AC into pulsating DC during one off cycle. That is, during positive off cycle it will going to convert, and during negative off cycle, so you'll be getting voltage zero. I think I have already shown here. You can see during positive off cycle it will going to conduct. Now it's zero because now it started. See, so this is for positive 11.3 you'll be getting, and again it's decreasing and it will going to become zero for negative off cycle. So for negative off cycle it will not convert AC into pulsating DC, and for positive off cycle it will going to convert AC into DC. Now what you should do here, as I said, that you need to consider, you need to measure two important parameter. You need to calculate two important parameter, that is efficiency, and one more is what, ripple factor. And to calculate efficiency and ripple factor, we are going to measure only one parameter from this waveform. What is that parameter? So that is the maximum voltage. So you need to measure what is the maximum voltage. I said already the maximum voltage is 11.3. So that is the maximum voltage. So just measure the maximum voltage, that is your VM. So from that VM you can easily calculate efficiency and ripple factor. So that is all about off-wave rectifier. If you see off-wave rectifier, like what is the advantage of off-wave rectifier? So this off-wave rectifier is very the circuit is very simple. We are using only one diode. When it comes to cost wise, it is very less. I mean the cost is less. You can easily design. But there are some the major drawbacks. You can't use off-wave rectifier to design a power supply, because in the power supply you need a continuous signal. But here what's happening in the case of off-wave rectifier, it's for positive off cycle it is converting, for negative off cycle you are not getting. So that's the disadvantage. Because of this reason, efficiency of off-wave rectifier is very less. So now this is a 3D view. This this is a virtual view. In similar way the components will looks like. Okay. So if you see 2D view, this is the 2D view. This is the 2D view, and this is our transformer. This is source I'm providing, and this will be primary of your transformer, and this will be secondary of your transformer. You can see there is a series connection here where diode is actually connected series with respect to secondary, and as well as what load. And this is your 2D view, and this is your 3D view. This is how your components looks like, the virtual in a virtual way. Okay. And so I just want to tell one more thing, like whenever if you want positive the DC, while if you are designing positive power supply, positive DC, then this connection is fine. Suppose sometimes you may require negative also, like I have sometime we need plus 5 volt, sometimes we need minus 5 volt. What to do for that? So for that, very simple, you should change the diode direction. That's it. If you change the diode direction, I will show you that. Let's rotate this. Just change the diode direction. Now you will be getting negative off cycle. You can see here what happens during positive off cycle it will conduct, and during negative off cycle it will not. For positive off cycle it will going to block, and for negative off cycle it will going to conduct. So So this we can also call it as a positive clipper, where positive off cycle is clipping, hence it is called as what, positive clipper. So off-wire rectifier is the best example for a positive and negative clipper. You will study positive clippers and clampers in analog electronics, theory, and as well as what, lab. So we use clippers and clampers in communication system to in order to signal shaping, and in order to shift the signal level, we are going to use clippers and clampers. And again, there also the diode. So diode will plays a major role in both the both clippers and as well as what, clampers. So that is an application of diode again. See here again the same thing. I'm getting here, instead of positive voltage, I'm getting negative voltage, because the voltage what we're getting here minus 11.3 again. So what about that voltage, the remaining voltage? The remaining voltage is clip off. So because there is a diode here, the diode is having some cut-in voltage again. When cut-in voltage will come actually, so the cut-in voltage will come during forward biasing condition again. So during positive off cycle you will be getting 0, and during negative off cycle you will be getting some voltage. You can see that also. So now I'll just keep here. Now we are getting some voltage. Now it is reducing. See, it will reaches to 0. Yes, it reaches to 0. When it reaches to 0, for positive off cycle it will going to become 0, and for negative off cycle you can observe the sign. So that sign indicates what? Yes, it is passing negative off cycle. See the sign, you please observe the sign, and the direction, you please observe the direction. This is the direction, current direction is flowing in a volta. So in a reverse direction, the current is flowing. That you should understand. It passing what, negative off cycle. Okay, and in order to find out the efficiency and ripple factor, as I said, like you just measure that Vm like 11.3. So that is a Vm, and you just use some formulas to calculate efficiency and ripple factor. You already derived efficiency and ripple factor in basic electronics. The simple calculation is there, so that you can find out efficiency and ripple factor. I think efficiency is PDC by PAC. And if you convert efficiency in terms of voltage, if you write that efficiency equation in terms of voltage, you will be getting efficiency will be equal to VDC by VRMS whole square. And you all know VDC is equal to Vm by pi for your off-wire rectifier, and VRMS will be equal to Vm by root 2. And if you take the ripple factor will be equal to square root of IRMS by IDC whole square minus 1. Anyhow, if the current is not there, then you can represent that equation in terms of voltage, and you can calculate efficiency will be equal to square root of the same thing, VDC by VRMS whole square minus 1. You can use that equation also to calculate efficiency and ripple factor. Now this is a simple simulation of rectifier. Again, I will tell you, this is the 3D view, how your components looks like, and virtual components actually, and this is the 3D view. Sorry, this one is the 2D view, and the diode is reversed. Definitely you will be getting negative voltage, and when the diode is if I change the diode direction again, you will be getting positive voltage. Again, depending upon your application, depending upon your requirement, we can design rectifiers. So this is one rectifier. Okay, this is one type of rectifier. So I'll stop at this point. So thank you so much.